Okay, so we talked about um, diffusion in the last video, and so a big part of that is water potential. And then water potential, it measures the effect of the solute concentration and pressure on the ability of the solution to diffuse. It determines the direction of the movement of water, and because it determines the ability of a water to diffuse, water flows from region of higher water potential to present regions of lower water potential. And so basically, water potential is the potential of water to move out of that area. So if a solution has a high water potential, there's a high, the water wants to move out of it really, really, really bad. And if it's low, it doesn't want to move that bad. And water potential is abbreviated as this trident thingamabob. It's called psi, like psi. And um, it's in megapascals, which is a measure of pressure. And psi is equal to 0 megapascals for pure water at sea level and at room temperature. That's just a constant that we should all know. Okay, so since both pressure and solute concentration affect water potential, the general equation for water potential is the water potential is equal to solute potential plus pressure potential. And so the pressure potential is usually given, it's like the pressure in the room and stuff, but the solute potential you need to calculate. And again, the pressure potential is a physical pressure on a solution, and in plant cells, the special name for pressure potential is a turgor potential because as water comes into the cell, the pressure is the pressure that the cell wall exerts back onto the cell. So it's the pushing back that the cell wall does when the cell wall itself is pushed out, and that's called the turgor pressure. And the protoplast is the living part of the cell. So I'm just going to talk about water potential and how it changes. So adding solutes makes the water potential lower, and you'll see why when we look at the equation in just 1 second. And so it makes it lower, so because now that the left side is greater than the right side, the water goes from the left to the right. When you add pressure, the water potential increases, so it goes from that side to from the right side to the left side. And then you could balance these out until you make it equal again. And because there's solute and he's putting pressure on this, then it balances out and they're just equal. But in this one, they're putting negative pressure, which means they're sucking it out, and that means that it's gonna have a lower water potential and it's gonna go this way. So I'm just gonna look at the equation real quick, and this is the equation for water potential. Um, For solute potential is equal to negative I CRT, and I is the ionization potential, which is the number of ions that can be made from the compound that you're looking at. So for NaCl, since it could be split into NaNCl, I is equal to 2. Since calcium chloride, since it's CaCl2, it can be split into 3 ions, I is equal to 3. Sucrose is just one big molecule, so I is only 1. C is the concentration of the things that you're looking at. So if it's the concentration is 0.1, in this case you plug in 0.1, if it's 0.2 you plug in 0.2, and so on. R is the gas constant, and that will be given, and T is the temperature in Kelvin. And so in a plant cell, whenever water flows in, the pressure, the turgor pressure of the cell wall will equal it out until the water potential becomes 0 again. So the initial cell has a pressure potential of 0 and a solute potential of negative 0.7, so the total water potential is negative 0.7. When put into pure water, because pure water has a water potential of 0, water flows from high to low water potential, so it flows into the cell. And then the cell, as the cell fills up, as the cell wall is stretched, it's going to start pushing back, and the turgor pressure is going to equal the solute potential, and then Since 0.7 minus 0.7 is equal to 0, the total water potential is 0, which means water is going to stop moving in and out. And in this one, when it's put into 0.4 sucrose solution, the water is going to start moving. The solute potential, when you calculate it, you get negative 0.9, and so that goes from high to low. Water is going to move from inside the solution to outside. And then, like I said, the cell's going to be plasmolyzed because water's moving out, so it's going to pull in on the cell walls and become this limp, really sad thing, and the water potential is going to become negative 0.9 to match the outside. And so here's just an example of a calculation that you should be able to do. This is a really easy one. If they tell you to find the solute potential given all the information, you just plug and chug. So I is equal to 2 because it's NaCl. They give you the concentration. The gas constant's given, and you plug in the temperature, and you get the answer. And the answer is always going to be in bars, which is a unit of pressure. If the concentration of NaCl inside the plant cell is 0.15, which way will the water diffuse if the cell is placed into the 0.1 NaCl solutions? So inside it's 0.15 and outside it's 0.1 molar. So in the last video I discussed how it goes from lower molarity to higher molarity because it goes from a higher concentration of water to a lower concentration of water. So it would go from 0.1 to 0.15, so it would go from the outside to the inside. And if you think about it, since it's 0.1 molar of sucrose, it's 0.9 molar of water, and since it's 0.15 molar of sucrose, it's 0.85 molar of water, so it's still going from high to low concentration of water. And in this one, what was the turgor pressure equal, so the plant pressure, equal if there's no net diffusion between the solution and the cell. So outside the cell, because it's placed in a 0.1 molar sodium chloride solution, the water potential of the solution is negative 4.95 bars as we calculated in 1a. And then that's going to equal the turgor pressure plus the solute potential of the cell. And because the concentration is 0.15 in the cell, you can calculate the solute potential, and you plug in negative 2.15 for the concentration and so on and so forth, and you get negative 7.4 bars. So you plug in negative 7.4 bars here and negative 4.94 bars for the water potential outside the solution, and you just solve for the turgor pressure. And when you do it, because it's a simple equation, you get 2.45 bars. And those are just some simple calculations for water potential that you should know how to do. You should especially know how to do 1A because it's easiest, but